space is cold. Everyone knows that, right? A near-perfect vacuum, millions of miles wide, sitting at around minus 270 degrees Celsius. For decades, scientists assumed nothing could get colder than that. That was nature's floor, the absolute limit. But what if I told you that limit isn't real? That somewhere in our own galaxy, there exists an object colder than the vacuum of space itself? Meet the Boomerang Nebula. At first glance, it looks like just another cloud of gas. Nothing extraordinary. But then the instruments spoke, and what they revealed shocked astronomers to their core. Temperatures colder than the cosmic background? Impossible. And yet, here it was. Scientists first thought it was an error. Instruments fail. Measurements glitch. But every observation confirmed the same chilling truth. This nebula is impossibly cold. And it gets even stranger. The gas doesn't drift slowly like other nebulae. Parts expand at unprecedented speeds. Some glow faintly, others remain frozen. Every attempt to explain it creates more questions than answers. So the question is, how does something in space become colder than space itself? What mechanism drives this extreme cooling? And if one nebula can break the cosmic rules so dramatically, what else might be lurking in the darkness, waiting to defy our understanding? In this video, we're going to break down the science, reveal the mysteries, and explore why the Boomerang Nebula is forcing scientists to rethink everything they thought they knew about the universe. To truly grasp why the Boomerang Nebula is such a cosmic anomaly, we need to understand the concept of cold in space. Space isn't simply empty and freezing. Its temperature is determined by the motion of particles. The fewer the particles, the less energy they carry, and the colder the environment. But even in near vacuum, particles retain some energy left over from the birth of the universe. This residual energy sets the cosmic microwave background temperature at roughly 2.7 Kelvin. For decades, this was considered a baseline, the practical coldest natural environment. Nebulae, clouds of gas and dust that drift through galaxies, are never colder than this baseline. Radiation from nearby stars, collisions, shock waves, or residual heat from stellar processes keeps them slightly warmer than the cosmic background. Yet, when astronomers pointed sensitive instruments at the Boomerang Nebula, the readings were shocking. Parts of the nebula measured around 1 Kelvin, colder than the surrounding universe. This wasn't a minor anomaly. It was a direct challenge to our understanding of physics. But temperature isn't the only strange feature. Unlike typical nebulae, whose gas moves slowly and predictably, the Boomerang Nebula's gas expands at extreme speeds, creating an environment that is far from stable. Some regions emit a faint glow, while others remain entirely frozen. The combination of extraordinary cold and rapid expansion makes it a unique laboratory for extreme physics. To put it in perspective, imagine the coldest freezer you've ever seen, then remove it from the Earth, send it across 5,000 light-years, and somehow make it colder than the vacuum around it. That's the scale of mystery astronomers faced. So how does a nebula become colder than space itself? What cosmic processes could allow this to happen? And what does this reveal about the limits of natural law in the universe? In the next section, we'll dive deeper into the star at the center, the engine behind the nebula's bizarre behavior. You'll see how one dying star could produce conditions that stretch the rules of physics and why scientists are still scratching their heads over this incredible cosmic enigma. At the heart of the Boomerang Nebula lies a star unlike any astronomers had seen. Unlike young stars, pulsars, or typical dying stars, this one behaves in ways that defy expectation. Normally, a star like our Sun approaches the end of its life gradually, shedding its outer layers to form a planetary nebula. The gas drifts outward, illuminated by the remaining core, cooling slowly over time. The process is stable, predictable, and well understood. The Boomerang Nebula's star, however, does the opposite. Observations reveal that it expelled an enormous amount of material in a surprisingly short period, violently ejecting gas at speeds exceeding 160 kilometers per second. That's not just unusual, it's extraordinary. Stars of this type almost never shed mass so rapidly or efficiently. This rapid expulsion is key to the nebula's extreme cold. As gas is flung outward, it expands rapidly. and rapid expansion leads to rapid cooling, a principle called adiabatic cooling. It's the same effect that makes a compressed spray can feel icy when released, but magnified on a cosmic scale. The result? Temperatures dropping below the cosmic background, reaching around 1 Kelvin in some regions. Yet even this explanation only partially solves the mystery. For the star's gas to reach these temperatures, timing, speed, and density must align perfectly. Any slight deviation would prevent the extreme cooling. It's as if the universe performed a precision experiment, and we happen to witness it at the exact right moment. Some astronomers speculate that the star may have had a companion, another star or massive object whose gravitational interaction triggered the violent mass ejection. This could also explain the nebula's hourglass shape and symmetrical structure. But so far, no companion has been observed directly. Theories remain speculative, leaving the exact mechanism unresolved. This star is also in a brief transitional phase, lasting only a few thousand years. In cosmic terms, that's a blink of an eye. Observing it requires incredible luck, precision, and timing. One missed window, and the opportunity to witness such extreme physics vanishes. The Boomerang Nebula might be the first we've seen, but it may not be the only one in the galaxy. Every detail of this star challenges our understanding of stellar evolution. Its mass loss rate, its efficiency, and its rapid cooling push the limits of known physics. The Boomerang Nebula is not just a cold cloud. It's a stress test for thermodynamics, stellar physics, and cosmic timing. In the next section, we'll explore how this violent ejection interacts with the surrounding gas, creating conditions colder than space itself, and why these fleeting phenomena are so difficult to study. So how does the Boomerang Nebula become colder than the space around it? The answer lies in a combination of physics, timing, and cosmic precision. At its core, temperature is determined by the motion of particles. The faster particles move, the hotter the object. The slower they move, the colder it becomes. In space, where particles are already sparse, controlling temperature is a delicate balancing act. Normally, a nebula absorbs energy from surrounding starlight and cosmic background radiation. This prevents temperatures from dropping below the 2.7 Kelvin baseline. But the Boomerang Nebula avoids reheating almost entirely. Its dense inner regions act like a shield, blocking external energy and preventing the gas from absorbing heat. At the same time, the star's violent ejection flings gas outward at extreme velocities. As the gas expands rapidly, it loses kinetic energy, cooling dramatically. This is the same principle that makes a spray can icy, only scaled up across light years of space. This process is known as adiabatic cooling, and it's central to the nebula's extreme temperatures. But here's the twist. Even adiabatic cooling alone shouldn't produce temperatures below the cosmic background. The Boomerang Nebula requires perfect alignment, the right density, expansion rate, and timing. Any deviation and the gas would remain warmer. The nebula's hourglass shape also plays a role. Directional ejection focuses the expansion along narrow paths, enhancing the cooling effect in certain regions while leaving others slightly warmer. This explains why some parts glow faintly while others are nearly frozen solid. It's a natural experiment happening across thousands of kilometers in space, and we're lucky enough to observe it. Even more surprising, this extreme cooling is temporary. Over time, the gas will thin out and radiation will seep in, warming the nebula back toward equilibrium. The Boomerang Nebula exists in a brief cosmic window, where extreme physics is visible before it vanishes. This fleeting nature makes it incredibly difficult to study, yet offers invaluable insight into the universe's hidden extremes. In essence, the Boomerang Nebula demonstrates that temperature is not fixed. It's influenced by motion, density, isolation, and timing. Under rare conditions, matter can temporarily fall below the cosmic baseline, revealing a level of cosmic engineering that seems almost impossible. Next, we'll uncover the structure and mysterious shapes of the nebula, exploring how geometry and velocity combine to produce one of the strangest cold environments in the universe. The Boomerang Nebula isn't just cold, it's also strikingly structured. Unlike typical nebulae, which often appear roughly spherical, this one has a distinct hourglass shape. Its gas flows outward in two opposing lobes, creating a symmetrical pattern that immediately caught astronomers' attention. Why does this matter? The shape isn't just cosmetic. It directly affects how the nebula cools. The directional outflow focuses gas along specific paths, amplifying the adiabatic cooling effect in those regions. The fastest expanding gas cools the most, reaching temperatures lower than the surrounding cosmic background, while slower-moving areas remain slightly warmer. This creates a stark contrast, a frozen cosmic sculpture where extreme cold and faint glow exist side by side. Even more intriguing is the velocity of the gas. Observations show that some regions move at speeds exceeding 160 kilometers per second. This isn't slow drift, it's violent, targeted expulsion. The combination of speed and geometry is critical. Rapid expansion alone would cool the gas, but without the hourglass structure, the effect would be diffused and temperatures wouldn't drop so dramatically. Astronomers also noticed subtle asymmetries. While the lobes are mostly symmetrical, slight variations hint at additional forces at play. Some theorists suggest a hidden companion star or massive object could have influenced the ejection, adding twists and irregularities to the otherwise ordered pattern. Yet no such companion has been observed, leaving the mystery unresolved. The Boomerang Nebula's structure also reveals how dynamic and transient cosmic phenomena can be. Its form is shaped not by slow, gradual processes, but by extreme, short-lived events. This is why catching it at the right time is so critical. Even small delays in observation could mean the difference between witnessing extreme cold and seeing a typical nebula. Moreover, the nebula isn't static. The expelled gas continues to move outward, interacting with surrounding interstellar material. Shockwaves, density variations, and radiation shielding all combine to maintain the extreme cooling, albeit temporarily. These interactions create a constantly evolving environment where temperature, motion, and density are in delicate balance. The nebula's dynamics also offer insight into stellar evolution. Observing such extreme mass loss and directional ejection challenges existing models. How often do stars undergo such violent transitions? Are we seeing a rare event, or one that occurs more frequently but goes unnoticed? The Boomerang Nebula suggests that transient extremes may be more common than we think, hidden in the vastness of space. Finally, its structure demonstrates the interplay between motion, timing, and geometry. Every feature, the lobes, the asymmetries, the expansion rate, contributes to its extreme cold. This cosmic dance, brief and fleeting, gives astronomers a unique window into the limits of physics, and why understanding shape and motion is just as critical as understanding temperature. Next, we'll dive into the chemical composition of the Boomerang Nebula, revealing how molecules survive and behave in the coldest known natural environment. The Boomerang Nebula isn't just cold and beautifully structured, it's also chemically bizarre. Most nebulae have predictable molecular compositions, dominated by hydrogen, helium, and traces of common molecules like carbon monoxide. But the Boomerang Nebula defies these norms. Spectral analysis reveals unexpected chemical signatures in its coldest regions. Molecules that normally break apart at higher temperatures appear intact, hinting at an environment that preserves delicate structures under extreme conditions. This raises immediate questions. How can molecules survive near 1 Kelvin? How do reactions proceed when energy levels are so low? One theory focuses on shielding effects. The dense inner regions block external radiation, creating a temporary sanctuary for molecules. Here, reactions occur at a glacial pace, unlike the more dynamic chemistry in warmer nebulae. This isolated chemistry is a rare laboratory, allowing scientists to witness molecular behavior in conditions nearly impossible to replicate on Earth. Yet even this doesn't fully explain the strange molecular abundances observed. Certain compounds appear in higher quantities than expected, while others are almost entirely absent. Some suggest the rapid expansion and extreme cooling itself may favor unusual chemical pathways, producing molecules that wouldn't form under normal circumstances. The nebula's molecular mysteries also reveal a deeper truth about the universe. Even seemingly simple elements behave unpredictably under extreme conditions. Hydrogen, carbon, and oxygen, common building blocks of stars and planets, can interact in surprising ways when energy, density, and time align perfectly. The Boomerang Nebula becomes more than just a frozen cloud. It's a cosmic chemistry experiment, unfolding naturally over thousands of years. And here's the twist. This chemistry is transient. As the nebula warms and disperses, these unusual molecules may break apart or react, leaving little trace behind. The universe could be producing countless chemical experiments like this, but only a lucky few, like the Boomerang Nebula, are visible to us at just the right moment. Finally, these molecular insights challenge astronomers' models of stellar evolution and interstellar chemistry. If extreme conditions can preserve or even create unusual molecules, what else might be happening in other cold, transient regions of space? Could there be chemical processes we've never imagined, hiding in fleeting cosmic windows? The Boomerang Nebula teaches us that chemistry in space isn't static. It's dynamic, fragile, and deeply tied to extreme physics. Every molecule, every reaction, tells a story about motion, timing, and energy, an intricate dance unfolding far beyond Earth. Next, we'll explore the philosophical and scientific implications, examining how the Boomerang Nebula challenges everything we thought we knew about the universe. The Boomerang Nebula isn't just a frozen curiosity. It's a challenge to our understanding of physics and astronomy. Scientists long assumed that the cosmic microwave background sets a practical lower limit for temperature in space. Anything colder was considered nearly impossible. Yet this nebula defies that expectation, proving that nature can temporarily bend these rules. Why does this matter? Because if a nebula can drop below the background temperature, then our models of thermodynamics and stellar evolution need revisiting. Current theories predict how stars lose mass, how gas cools, and how molecules behave. The Boomerang Nebula exists at the edge of these predictions, revealing gaps in our understanding. Take mass loss, for instance. Most dying stars shed their outer layers gradually, over thousands or millions of years. The Boomerang Nebula star did the opposite, expelling gas violently and at extraordinary speeds. This extreme, short-lived event creates the perfect conditions for adiabatic cooling, yet the efficiency is far beyond what standard models allow. If this can happen once, it could happen elsewhere, possibly more frequently than we realize. Its existence also raises questions about the limits of observation. Astronomers typically study stable objects that change slowly over time. But fleeting phenomena like the Boomerang Nebula suggest that the universe may be full of rare, extreme events that slip past our instruments, invisible until just the right moment. This challenges us to rethink not just what we know, but how we know it. Then there's the philosophical angle. The Boomerang Nebula reminds us that laws of physics are not static boundaries. They're flexible, dynamic, and can produce extreme outcomes under precise conditions. Expansion, timing, shielding, and geometry all interact in ways that temporarily create environments previously deemed impossible. This isn't a violation, it's a natural stress test for the universe's rules. The implications extend beyond thermodynamics. Stellar evolution models, molecular chemistry, and cosmic structure formation may all need adjustment to account for rare, transient extremes. Even the distribution of cold nebulae across galaxies could be different than previously assumed, hidden because they exist only briefly. Finally, this nebula forces a broader reflection on scientific humility. The universe has a way of surprising us, of presenting conditions that challenge our assumptions. Observing the Boomerang Nebula isn't just a technical achievement. It's a lesson in patience, timing, and the limits of human knowledge. It teaches us that discovery isn't just about seeing, but about catching the universe in motion at exactly the right moment. In essence, the Boomerang Nebula is a cosmic wake-up call. It's proof that the universe isn't confined by our expectations. It operates on principles that sometimes produce fleeting extremes, testing theories, models, and human understanding alike. And while one nebula may seem small, its lessons ripple across the fields of physics and astronomy, reshaping how scientists study extreme environments and rare phenomena. Next, we'll dive into the final section, Why the Boomerang Nebula Matters to Us, where we connect cosmic extremes to our understanding of the universe and the thrill of discovery itself. At first glance, the Boomerang Nebula might seem distant, cold, and irrelevant to daily life. It's 5,000 light-years away, a fleeting speck in a vast galaxy. Yet its significance goes far beyond its size or location. It challenges the limits of human knowledge and curiosity. The nebula is a reminder that science is not just about facts, but about discovery. Every extreme, fleeting event like this is a window into possibilities we hadn't imagined. By observing it, we learn that the universe isn't static. It's dynamic, unpredictable, and capable of producing conditions that test even our most established theories. Consider this: the Boomerang Nebula temporarily defies the cosmic microwave background temperature, the very baseline of the universe's cold. This teaches us that nature has a way of bending expectations, producing phenomena that seem impossible until we witness them. For scientists, this is exhilarating. For curious minds, it's a reminder that the universe is stranger and more complex than we can intuit. The implications extend beyond science. Observing rare, extreme events encourages patience, precision, and attentiveness, skills that apply to life itself. It shows the importance of timing, of being ready when opportunity arises. If astronomers had not been prepared, this fleeting cosmic moment would have gone unnoticed, and the secrets of extreme cooling would remain hidden. Moreover, the nebula fuels our imagination and sense of wonder. It's a frozen laboratory where physics, chemistry, and motion collide in ways we can barely comprehend. Every molecule, every blast of cold gas, every unusual chemical reaction tells a story about the universe's capability to surprise us. It reminds us that even in a cosmos governed by laws, the unexpected is always possible. Finally, the Boomerang Nebula inspires the next generation of explorers, thinkers, and scientists. Its story encourages curiosity-driven learning, showing that knowledge isn't just accumulated. It's actively uncovered through observation, experimentation, and the courage to ask uncomfortable questions. In the end, the Boomerang Nebula matters because it connects the human mind to the vastness of the cosmos. It demonstrates that the universe is alive with rare, fleeting phenomena that push boundaries, challenge understanding, and ignite imagination. By studying it, we don't just learn about extreme cold. We learn about the thrill of discovery, the power of observation, and the endless possibilities waiting in the universe. The Boomerang Nebula is more than a frozen cloud of gas. It's a message, a natural experiment, and a cosmic teacher, reminding us that the universe is full of secrets, waiting for those who are ready to watch, question, and understand.